What if the universe itself is rigged for us to exist? Today, we're diving deep into one of the most mind-bending ideas in all of science and philosophy, the Anthropic Principle. The staggering notion that reality must permit observers like us to exist, and that this single fact might explain everything we see around us. Visionary thinkers like philosopher Nick Bostrom have pushed this even further, daring to ask whether our entire reality could be a digital reconstruction, an ancestor simulation engineered by some advanced civilization operating on a level we can barely imagine. And then there's the terrifying doomsday argument, which claims that pure statistics alone could predict the extinction of humanity. Not from war, not from disaster, but simply from the mathematical odds of when you happen to exist on the grand timeline of our species. Every one of these explosive questions about the end of the world, the origin of creation, and the very nature of existence springs from the same haunting puzzle. What does it truly mean that we are here to ask them at all? These ideas share two remarkable traits. First, they are breathtakingly provocative, because at their core they're asking, is there a God? Is any of this real? And are we already doomed? Second, they make for extraordinary thought experiments, because they are nearly impossible to prove or disprove with the data we have, and gathering more relevant data is brutally difficult. That's the razor's edge of the Anthropic Principle and the Copernican Principle. Both force us to draw meaningful conclusions from almost nothing. We can't collect samples from other universes with different physical constants. We can't peek behind the curtain of a possible simulation. We can't leap forward in time to read humanity's final census record. At the heart of all three mysteries runs a single powerful thread, the Anthropic Principle. The revolutionary idea that observation itself acts as a cosmic filter. You can only witness events if you are present for them, and sometimes the very reason you exist is inseparable from the reason those events unfolded the way they did. Science itself was born from this kind of humility. Copernicus shattered the ancient illusion that Earth sat at the center of everything. Galileo delivered the stunning revelation that the same laws governing falling objects here on Earth also govern the motion of planets across the heavens. You fall to the ground for the exact same reason planets orbit the sun. Science almost always begins by admitting we are not special, not central, not the point. That radical shift started with Copernicus, who dethroned our world from the heart of the cosmos, and in doing so, cracked open the universe for everything that followed. Centuries later, telescopes and the laws of physics sealed the deal, revealing that we're just one pale blue dot, orbiting an ordinary star inside an average galaxy, drifting through a universe so vast it defies imagination. That mindset crystallized into what's known as the Copernican Principle, or more broadly, the mediocrity principle. If there's no reason to believe we're special, we should assume we're typical. At its core, the more data you collect, the clearer the picture becomes of just how normal or how rare you actually are. But imagine you've only ever met one human, and that person is 7 feet tall. You'd be dead wrong to call them average, yet that's exactly what the Copernican Principle would suggest. Pull 100 random people and pick one from the crowd, and chances are they'll be pretty ordinary. It's a solid strategy when the data is scarce. Sure, more data is always better, but even then you could stumble upon 100 people in a row, each sitting in the top 1% of human height. The odds? 1 followed by 200 zeros. Staggering, but not impossible. And inevitably, someone somewhere is going to draw that statistically absurd hand. Roughly 1 in 1,000 people will flip a coin 10 times, land heads every single time, and walk away convinced the coin is rigged. And if you landed on Earth and found yourself surrounded by a crowd of giants, the smart move would be to ask, did something filter this result? Did you accidentally crash a basketball tournament? Here's the thing. Both the mediocrity principle and the anthropic principle, despite sounding like grand cosmic philosophy, are actually deeply familiar everyday ideas. Think about it. Many of us have friends or partners who seem statistically impossible, sharing way too many interests to be coincidence. But it wasn't coincidence at all. You and your friend both love comic books, and you met at a comic store. Hardly a random encounter. You both obsess over tabletop games because they pulled you in years ago and you never looked back. And if you surveyed a random crowd, maybe 1 in 10 likes comic books, 1 in 20 loves tabletop gaming. By pure chance, you'd expect only 1 in 200 to love both. But in reality, it's closer to 1 in 40 because those interests naturally overlap. There's a pattern, a correlation. What makes cosmic scale examples feel so much deeper is the sheer scale and the brutal difficulty of gathering more data. Without powerful telescopes, there was only one Earth-like planet in sight, this one. So by the mediocrity principle, it must be average. If there's only one species like ours, we're probably the norm. It's not arrogance. It's actually the opposite. It's a form of reasoning that says, assume we're ordinary until something proves otherwise. Then the anthropic principle steps in and politely pushes back. It argues that when you're trying to understand why the universe looks the way it does, you simply cannot treat yourself as a random observer. Because the very fact that you can observe anything at all depends entirely on the conditions that made your existence possible. It's a subtle shift in perspective, but the implications, absolutely enormous. If the universe were even slightly different, if gravity were stronger, stars would burn out in a fraction of the time. If the electromagnetic force were just a little weaker, atoms wouldn't hold together at all. A cosmos like that wouldn't just lack life, it would lack anyone capable of even asking the question. So when we look out and marvel that everything seems perfectly tuned for us, the anthropic principle quietly steps in and says, of course it does. In any universe where it wasn't, there would be nobody left to wonder why. That's a breathtaking idea. But it's also a deeply dangerous one. Because the moment you start explaining things by saying, we exist because we can, you risk collapsing a profound scientific mystery into a circular argument. It becomes the ultimate just so story. The universe must look this way, or we wouldn't be here to notice. And while that's logically airtight, it tells you absolutely nothing about why it actually is that way. And here's the critical point. Logical coherence does not make something true. The greatest leap forward in human history wasn't philosophy. It was the realization that you have to go out and gather real data. Because time and again, what seemed perfectly reasonable in theory turned out to be completely wrong the moment actual evidence came in. That same limitation, remarkably, would apply even to a superintelligent AI. Raw intelligence alone cannot conjure scientific breakthroughs out of thin air. It still needs experiments, still needs data from the real world. This is precisely why, when examining the Fermi paradox, the most compelling explanation remains that intelligent technological life evolves extraordinarily rarely. Not a perfect answer, but arguably the least flawed of all available options. Knowledge of other worlds remains frustratingly thin. Even our understanding of life's history on this very planet is riddled with gaps. Without that deeper foundation, bold conclusions simply don't hold up. And the sheer volume of unexplained phenomena, poorly understood processes, and unknown unknowns makes it entirely reasonable to suspect that some of our most fundamental assumptions about life and the universe are simply wrong. That's what makes the anthropic principle so uncomfortable. It sits right on the border between science and philosophy. It's not a theory of how the universe works. It's a lens for reasoning when gathering more data is nearly impossible. A way of asking, given everything I cannot observe, what can I even conclude? That's what makes it so powerful and so dangerously easy to misuse. It reminds us our perspective is inherently biased just by virtue of existing, but it also tempts us to use that bias as an excuse to stop searching for deeper answers. And that leads us straight into one of the most controversial ideas in all of modern thought, the doomsday argument. It takes anthropic bias, injects cold hard statistics, and arrives at a genuinely unsettling claim that we can predict humanity's fate simply from our own position in the timeline. But to truly understand it, we first need to unpack what probabilistic reasoning actually means, and why it can both illuminate and catastrophically mislead us when applied to questions as enormous as the future of the human race. The anthropic principle itself was first formally named by astrophysicist Brandon Carter in 1973, fittingly, at a conference honoring Copernicus. The underlying concept had been quietly gestating for much longer, with early traces visible in the thinking of Leibniz, Kant, Boltzmann, and others who dared to ask why the universe is the way it is. Carter formalized it, and his background in cosmology shaped the way he framed the idea, not as a mystical statement about purpose, nor as a mundane observation about being present to witness something anomalous. Instead, it became a practical tool for reasoning about a universe we can barely sample. After all, astrophysicists spend their careers studying the largest systems imaginable, most of which they can never touch, visit, or replicate. So it's no surprise that Carter's formulation was about drawing conclusions from almost no direct data. It's also worth emphasizing that this is not quite the same as selection bias or the observer effect. Selection bias is like sampling the ocean with a fishing net. You miss everything too large or too small to be caught. The observer effect means your presence alters the experiment. Something cools in your shadow or warms from your body heat. The anthropic principle is something different entirely. Carter named it from the Greek word anthropos, meaning human, though he later admitted the term was a bit misleading. It's not about humans specifically, but about any observers at all. The principle comes in several flavors, but they all orbit the same core idea. The universe's apparent fine-tuning and our existence as observers are not separate facts. They are deeply connected. Carter divided it into two types. First, the weak anthropic principle, the modest version, which states that our observations of the universe are biased by the simple fact that we exist. We shouldn't be surprised to find ourselves in a universe capable of supporting life, because only such a universe could contain us. Every observation comes pre-filtered through our own existence. You cannot observe a dead universe. Second came the strong anthropic principle, the bold version, which claims the universe must allow observers to exist. That sounds almost teleological, as if the cosmos is somehow required to produce intelligence. Carter didn't intend it as theology, though it certainly became a popular theological talking point. He meant it as a statement of logical necessity. A universe that could never generate observers would never be known to exist at all. Later, cosmologists John Barrow and Frank Tipler expanded these ideas into what they called the final anthropic principle, a sweeping extrapolation suggesting that once intelligent life arises, it will never truly disappear. That intelligence will endure, adapt, and ultimately find ways to persist forever. This also connects intriguingly to quantum observer effects. Whether you read that as science, philosophy, or sheer optimism depends entirely on your mood, but it completes a stunning arc from modest observation all the way to cosmic destiny. Barrow and Tipler published a landmark book on these ideas in the mid-1980s, which introduced an entire generation of curious minds to concepts that blurred the line between physics and philosophy. It's worth noting that many popular physics books from that era, even well-known ones, turned out to be presenting fairly fringe theories dressed up as mainstream science. These ideas may sound familiar, but exploring them through the lens of physics and philosophy reveals just how deep the rabbit hole goes. What makes this fascinating is how philosopher Nick Bostrom took these concepts and formalized them in a groundbreaking way, cataloging over 30 distinct versions of the anthropic principle, from the purely pragmatic to the deeply metaphysical, and adding several powerful new ones of his own. This is exactly why the anthropic principle is so much more than just a cosmic curiosity or a near synonym for the fine-tuned universe argument. Two of the most compelling versions are the self-sampling assumption, or SSA, and the self-indication assumption, SIA, and they fundamentally reshape how we think about probability and observer selection. Under the self-sampling assumption, you should reason as though you are a completely random sample, drawn from all observers who actually exist. Your situation, where and when you find yourself, should be considered perfectly typical among those observers. You are just one unremarkable face in an enormous crowd. This is the chilling logic behind the doomsday argument, which suggests that if humanity were destined to produce trillions upon trillions of members, you would expect to find yourself somewhere deep within that vast timeline, not suspiciously close to the very beginning. Being this early implies a much smaller total population is coming. But this is also a striking example of probabilistic reasoning gone dangerously wrong, drawing sweeping universal conclusions from a single, narrow slice of data. The self-indication assumption flips everything on its head. It argues that your very existence is evidence favoring universes containing more observers rather than fewer. Think of it as a cosmic lottery where every conscious being is a ticket. The more tickets exist, the greater the odds that one of them is you. So if reality could be either a small, sparsely populated universe or a vast one teeming with countless civilizations, SciIA says the second option is dramatically more probable because it offers far more opportunities for your consciousness to emerge at all. If you have just two cities, one a quiet small town and one a massive metropolis, a randomly selected person is overwhelmingly more likely to come from that metropolis. In this breathtaking view, existence itself votes for abundance, for multiverses, for alien life, for simulated minds, for any scenario that multiplies the number of observers to the absolute maximum. This reasoning sounds wonderfully optimistic, until you realize it could mean that most conscious beings aren't biological at all, but artificial minds trapped inside simulations or alien machines. There's also a dangerous tendency in this line of thinking to treat our universe as naturally fertile ground for intelligent life. That assumption largely traces back to physicists in the 60s and 70s who defaulted to the idea that space travel was brutally hard while nuclear weapons were terrifyingly easy, and that this explained why we'd never heard from aliens. They were out there, far away, confined to a single world, and perhaps not for much longer. That was the original default answer to the Fermi paradox. But biologists have always been far more skeptical about life and intelligence emerging everywhere. Then, with the triumph of Apollo and the Cold War never erupting into full catastrophe, a new idea took hold that since life is essentially hardwired to explore and expand, any technological civilization that survives long enough will eventually figure out how to spread across the stars. And once scattered across many worlds, they become nearly impossible to destroy. This gave rise to our other dominant Fermi paradox solution, that since we see no one out there, spacefaring civilizations almost certainly don't arise very often. Without verified alien intelligence, a working interstellar spacecraft, or a functioning colony on another world, no position in this debate can truly claim strong evidence. Carter gave the concept its name. Tipler and Barrow expanded its reach. And Bostrom constructed the philosophical architecture around it. But other versions exist too, like the participatory Anthropic Principle, inspired by physicist John Wheeler, which suggests that conscious observation doesn't merely reveal the universe, but actually helps bring it into existence. Many schools of thought in quantum physics argue that a conscious mind must be involved in determining outcomes, like the fate of Schrödinger's cat. And unlike many such questions, this one is currently unprovable either way, because any observation we make inherently involves us making it. You could run a fully automated experiment, collect data, and leave it untouched for a century, but eventually someone has to look at those results. And the moment they do, a conscious observer is involved. Bostrom's most famous contribution, of course, is the simulation hypothesis, which reframes everything. Instead of asking why the universe's constants appear fine-tuned, it asks whether those constants were deliberately chosen by programmers, not by physics. This can easily be rephrased as the work of God or gods or unimaginably powerful intelligent beings. Functionally, it's identical. But framing it as a programmer somehow drains some of the emotional charge from the question, while letting us use video games and virtual reality as relatable examples. Though it's worth noting that the options available to a truly infinite being versus a very powerful but finite one differ enormously in what that creation might actually look like. An all-powerful being, for instance, would have absolutely no reason to limit or compress the inner life it grants to its background characters. At this point, the Anthropic Principle starts to look less like a single idea and more like a sprawling family tree of philosophical thought experiments. Some grounded, some wildly speculative, all wrestling with the same deeply uncomfortable realization that our existence is not a neutral fact. It actually changes what kinds of questions can even be asked. When you mix this kind of observer bias with statistics, you get something especially provocative, the doomsday argument. A mathematical attempt to predict humanity's entire future from our own place in the cosmic roll call. To understand how that reasoning works and why it's both fascinating and deeply flawed, we need to take a closer look at how probabilistic arguments function in science, and exactly where they can lead us dangerously astray. Let's start with simple examples before the cosmological ones. The Anthropic Principle can sound lofty and abstract, but it really describes something we all experience in everyday life, drawing conclusions from limited information while completely forgetting how much our own perspective shapes the sample. Imagine you're at an event and notice that everyone around you seems unusually skilled at mental math, oddly cautious about risk, and strangely obsessed with actuarial tables. You might think the entire world is packed with cautious number crunchers until you realize your sample came entirely from an insurance convention. The Anthropic Principle works exactly the same way. When we examine a set of samples, we must consider the possibility that the selection was never truly random, that it's fundamentally connected to our own presence. Think about it this way. A first contact with alien intelligence would likely involve people who are disproportionately curious and bold, because that's precisely who gets sent as explorers on both sides. The mediocrity principle and the anthropic principle are both reasoning tools designed for situations where data is painfully scarce. The first says, assume you're average until proven otherwise. The second says, remember, you can only ever sample from situations that actually allowed you to exist. Either way, you're navigating profound uncertainty. It's not unlike the Dunning-Kruger effect. When you know very little, you may feel dangerously overconfident. As you learn more, you begin to realize just how deep the unknowns truly go. Early knowledge breeds false confidence, a peak of certainty reached while still remarkably ignorant. Call it the peak of Mount Stupid. And honestly, most of us visit there from time to time. Some people seem to have built permanent cabins there. But here's what we must never forget. For all we think we know about the universe today, we've barely collected any hands-on data from anywhere beyond Earth. We don't actually know that our universe represents the sum of everything that is, was, and ever will be. The biggest question remains, why does everything look exactly the way it does right here, on this one pale blue dot? And with that humbling thought in mind, let's keep pushing deeper into the mystery. What is a Boltzmann brain, and why does it challenge everything we think we know about reality? In the late 19th century, physicist Ludwig Boltzmann proposed something truly mind-bending, that our ordered universe might simply be a rare statistical fluctuation in an otherwise chaotic cosmos. Given infinite time, even the most improbable events will eventually happen by pure chance. But here's where things get deeply unsettling. If that's true, why do we find ourselves inside a vast, structured universe instead of being a lone, momentary brain drifting through empty void, hallucinating a reality that doesn't even exist? Statistically, it would require far less energy and far less cosmic luck to assemble a single conscious brain, complete with false memories, than to construct an entire universe filled with billions of galaxies. And it would be even easier for some primitive self-organizing proto-mind to gradually build itself up, rather than for a full brain to appear all at once. Now, Boltzmann was working at a time when scientists assumed the universe was probably infinite in every direction and evenly distributed throughout. That assumption no longer holds. But the Anthropic Principle on a cosmological scale suggests there could be a vast multiverse of life-hostile universes, opening the door to timescales and possibilities far beyond our own Big Bang. What this really means is an enormous number of places where the laws of physics simply don't allow stable chemistry to exist in any meaningful abundance over long periods of time. Incredibly, we have absolutely no idea what the actual odds are for a life-friendly universe like ours to emerge, or what the minimum requirements for a Boltzmann brain even are. Both probabilities are almost incomprehensibly small. Some estimates suggest figures like 10 to the power of 120 for a finely tuned universe, staggering numbers tied to the cosmological constant. To put that into perspective, life-friendly universes would be rarer than a single atom compared to every particle in the entire observable cosmos. And calculating the odds of a brain assembling randomly, that can only be done within a reality that already permits our kind of chemistry, which itself represents a vanishingly tiny fraction of all possible universes. What's even more fascinating is that such a brain might not need to begin at human-level intelligence, or even as a complete brain at all. It might simply need the potential to expand and self-organize, a far easier random outcome than a fully formed mind appearing from nothing. And yet, there's absolutely no reason to assume a Boltzmann brain would start out sane. The overwhelming majority of such minds would almost certainly be utterly incoherent, lacking functional sensory organs, and trapped inside their own mad dreams, if they were unlucky enough to have any self-awareness at all, or the ability to keep themselves alive long enough to starve to death. So if we take pure probability seriously, most observers should be these fleeting, fractured minds, Boltzmann brains, not evolved beings like us. Yet we clearly experience a coherent world that persists whether or not we are paying attention. That suggests either our assumptions about probability are fundamentally wrong, or our universe is special in ways that rule those nightmare scenarios out entirely. Here's where it gets truly mind-bending. Imagine the odds of a self-growing mind forming around a stellar-scale power source, a Matryoshka Boltzmann brain, one that might begin no bigger than an amoeba. In simulation hypothesis terms, such a mind could meaningfully simulate untold quintillions of conscious minds and multiple full-scale universes. And it's not entirely unreasonable to assume its internal mental landscape might continuously reshape itself to feel perfectly consistent and real. Suddenly we're faced with a universe that is mostly vast, silent, and dead, versus a tiny, rare, but massively populated set of inner realities blooming inside rare Boltzmann megabrains. In that sense, Boltzmann brains reveal both the power and the peril of anthropic reasoning. Push it too far, and you can explain anything, even the most outrageous absurdities, simply because you happen to be there to perceive them. Though, of course, they might not actually be absurd at all. All things considered, it is probably wise rather than arrogant to assume that Earth and humanity are genuinely exceptional, not just a mediocre planet or species picked at random, while still humbly acknowledging that we might appear rather ordinary by the standards of other intelligent beings or life-bearing worlds we have yet to discover. For all we know, we might seem mediocre simply because we are literally the only sample that exists, not just the only one we've encountered. The Anthropic Principle lives in that charged space between ignorance and humility, where our knowledge of the universe is vast enough to ask the right questions, but still far too limited to expect final answers. Both it and the Copernican principle are crude tools compared to a proper analysis of larger datasets. But for now, they are all we have, besides our insatiable curiosity.